Welcome to Chapter 4, Floating Point Numbers. Chapter 3 gave you whole numbers in a fixed box, but so much of the world is fractions. A temperature of 36.6, a price of 19.99, a voltage of 3.3. In this chapter you will learn how a computer stores fractions, how to decode a real pattern by hand, and why fractions sometimes behave in surprising ways. Let's begin with a puzzle. Type 0.1 plus 0.2 into almost any programming language, and you expect 0.3. What you actually get is 0.3, followed by a long tail of zeros ending in a 4. That is not a bug. It is the honest cost of storing fractions in a fixed number of bits. By the end of this chapter, you will know exactly where those extra digits come from and how to write code that handles them safely. Let us look at the plan for this video. It has 4 parts. First, fixed point, the simplest way to store a fraction by locking the binary point at one agreed spot and the trade-off between range and precision that forces on you. Second, the centerpiece, the IEEE 754 standard, which lets the binary point float, using 3 fields called the sign, the exponent, and the mantissa. Third, special values, how the standard encodes 0, infinity, not a number, and the tiny subnormal values that live just above 0. And fourth, precision and pitfalls, machine epsilon, catastrophic cancellation, and how to compare 2 floating point numbers safely. Let us start with the simplest way to put a fraction into a fixed width box, fixed point. Integers are perfect for counting whole things, pixels, bytes, loop steps, but so much of what we measure is not whole. A temperature of 36.6, a price of 19.99, a sensor voltage of 3.3. Each of these has a part after the point that an integer simply throws away. To store a fraction in binary, you need a way to say where the point goes. The simplest answer is fixed point. You pick one spot for the point, and you never move it. This strip shows a fixed point format called Q4.4. 4 bits to the left of the binary point and 4 bits to the right. To the left, the place values are the familiar powers of 2, going up 8, 4, 2, 1. Here sits the binary point, the divider between the whole part and the fraction part. And to the right of the point, the pattern simply keeps having 1/2, 1/4, 1/8, 1/16. The picture is a mirror. Each step left doubles the value, and each step right halves it. That is the whole idea of a binary point. Now the practical problem. A register holds only bits. It has no place to keep a little dot symbol. So where is the binary point? In fixed point, the answer is a convention. You decide in advance where the point sits, and everyone who touches the data agrees. We write a format as the letter Q, then the number of integer bits, the 4 bits on the left here. Then a dot and the number of fraction bits, the 4 bits on the right. So Q4.4 means 4 integer bits and 4 fraction bits, packed into one 8-bit value. The hardware just stores an ordinary integer. The programmer remembers where the point belongs. Let us read the pattern 0101.1100 in Q4.4. The method is the same weighted sum you already know, carried across the point. On the integer side, the bit worth 4 is 1, so it contributes 4. The bit worth 1 is also 1, contributing 1, so the integer part is 5. Now cross the point. The first fraction bit is worth 1/2, and it is 1, so it adds 1/2. The second fraction bit is worth 1/4, and it is 1, so it adds 1/4. The last two fraction bits are 0, so they add nothing. Add the teal contributions. 4 plus 1 plus 1/2 plus 1/4 is 5.75. That is the value this pattern holds. Every fixed point format faces the same tension. You have a fixed number of bits, 8 here, and you must split them between the integer side and the fraction side. Q8.0 is just a plain integer. It reaches 255, but its step is a whole one with no fractions at all. Slide the point over to Q6.2, and you gain 2 fraction bits. The step drops to 1/4, but the largest value falls to about 63.75. Q4.4 gives 4 fraction bits, a step of 1/16, reaching about 16. Q2.6 gives 6 fraction bits, a finer step still, but the largest value is now under 4. And Q0.8 spends every bit on the fraction. The step is tiny, better than 4 thousandths, but the largest value is less than 1. Range and precision fight over the same bits. You cannot have both. Fixed point is a good tool when your values stay in a band you know ahead of time, audio samples, pixel coordinates, a sensor reading in a fixed range. It is simple and fast. But many programs must handle numbers at wildly different scales. The mass of an electron is about 9.1 times 10 to the minus 31 kilograms. The mass of the sun is about 2 times 10 to the 30th kilograms. A single fixed point format able to hold both would need roughly 200 bits, and almost all of them would be wasted at any one scale. The fix is to let the binary point float, so that precision follows whatever scale you are actually working at. That is floating point. This is the centerpiece of the chapter. IEEE 754, the floating point standard that virtually every processor and every language uses. Understanding its 3 fields is our goal. You already know decimal scientific notation. You write 6,022,000 as 6.022 times 10 to the 6th. Same significant digits, and the point floats to wherever the digits are. Binary scientific notation does exactly the same thing, but in base 2. Remember from the last section that 5.75 is 1.11 in binary. Normalize it by moving the binary point so a single one sits to the left of it. The point moves 2 places left, which makes the exponent 2, and the significand becomes 1.0111. The value equals the significand times 2 to the exponent. Floating point hardware stores exactly these pieces. An IEEE 754 number packs 3 fields into one fixed width bit string. Watch them appear, one at a time. First, assign a single bit. 0 means positive, 1 means negative. Second, the exponent, 8 bits in single precision. It controls the scale, that is, where the binary point sits, and it is stored in a special biased form we will unpack next. Third, the mantissa, also called the significand, 23 bits that hold the significant digits. The mantissa is the precision payload. More mantissa bits mean more significant digits. The sign bit is simpler than anything in Chapter 3. In 2's complement, the top bit carried a negative place value and interacted with the arithmetic. Here it does not. The floating point sign bit is a pure flag sitting alone at the far left. It just picks the sign through -1 to the power s when s is 0, that is +1. When s is 1, that is -1. So to negate a floating point number, you flip that 1 bit, no flipping every bit, no adding 1, no carry. The value is -1 to the power s times the magnitude. Now the exponent. It must cover both large positive powers and small negative ones, but the field itself is an ordinary unsigned group of bits. The trick is a bias. In single precision, the bias is 127. You store the true exponent plus 127, which keeps the stored value non-negative. To read it back, you subtract the bias. The true exponent equals e minus 127. Two stored patterns, all zeros and all ones, are held back and reserved for the special values in part 3. Now an elegant trick. When you normalize a binary number, the digit to the left of the point is always a 1, because 1 is the only non-zero digit binary has. If it is always 1, why spend a bit storing it? IEEE 754 does not. It leaves that leading one implicit or hidden and stores only the fraction bits. So a 23-bit mantissa field actually gives you 24 significant bits, 1 implicit, plus 23 stored, an extra bit of precision for free. When you decode, you must remember to put that leading one back on. Put the three fields together, and for a normal value, one whose exponent field runs from 1 to 254, you get one formula for the value. The value equals -1 to the power s, times 1 point mantissa, times 2 to the power of e minus 127. Read it left to right. The sign picks the direction plus or minus. The 1 point mantissa gives the significant digits, with that implicit leading 1 restored. And 2 to the power of the true exponent, the stored exponent minus the bias, sets the scale. 3 fields, 1 clean formula. One caution before we use it. This formula is only for normal values, those with an exponent field from 1 to 254. Subnormals, 0, infinity, and not a number are the special cases. Part 3 encodes them differently, and none of them uses this formula. Now let us run the formula on a real pattern. Take a real 32-bit pattern to decode. First the sign. The sign bit is 0. Then the exponent field, 1000010. Then the mantissa, which starts 101 and continues with zeros. We work through those 4 stages, sign, exponent, mantissa, and then combine them into the value. Let us do each stage carefully on the next slide. Stage 1, the sign. The sign bit is 0, so -1 to the power 0 is +1. The number is positive. Stage 2, the exponent. The stored field 1000010 is 130. Subtract the bias of 127, and the true exponent is 3. Stage 3, the mantissa. Restore the implicit leading one to get 1.101 in binary. That is 1 plus 1/2 plus 1/8, which equals 1.625. Stage 4, combine. 1.625 times 2 to the third is 1.625 times 8, which is 13.0. That is how a floating point pattern becomes a number. The same 3 fields come in 2 standard sizes. Single precision uses 32 bits, 1 sign bit, 8 exponent bits, and 23 mantissa bits. Double precision uses 11 exponent bits with a bias of 1023, instead of 8 bits with a bias of 127. It also uses 52 mantissa bits, 53 effective, instead of 23. More exponent bits push the largest value from about 3.4 times 10 to the 38th, all the way to about 1.8 times 10 to the 308th. And more mantissa bits raise the reliable precision from about 7 decimal digits to about 15 or 16. The cost is simply twice the storage. Double precision is the default in most languages, including Python, JavaScript, and C. We held back 2 exponent patterns as reserved. Now we spend them. They encode 0, infinity, not a number, and the subnormal values near 0. This table is the complete map for single precision, and the exponent field is the key that tells you which category you are in. A stored exponent between 1 and 254 is an ordinary normal number, the case we already handled. A stored exponent of all zeros with an all zero significand means 0. All zeros again, but with a non-zero significand, means a subnormal. A stored exponent of all ones with an all zero significand means infinity. And all ones with a non-zero significand means not a number, so the significand breaks each tie. Every single bit pattern lands in exactly one category. Nothing is wasted. Let us walk these rows one at a time. Start with the 0 row. When the stored exponent is all zeros and the significand is also all zeros, the value is 0. 0 needs its own special encoding, because the normal formula always includes that implicit leading 1, so it can never produce 0 on its own. Now the twist. The sign bit is independent, so there are 2 zeros, a positive 0 and a negative 0. IEEE 754 says they compare as equal, so plus 0 is equal to minus 0, even though their bit patterns differ. Most of the time you will never notice, but in a few careful calculations it matters. Next, the infinity row. When the stored exponent is all ones and the significand is all zeros, the value is infinity, and the sign bit chooses positive or negative infinity. And infinity here is not an error. It is a genuine value you can store, compare, and compute with. Under the default IEEE 754 mode, when a result grows too large to represent, that overflow produces infinity instead of crashing, and dividing a non-zero number by 0 gives infinity too. The program keeps running, and you can test for infinity afterward. Some languages raise an error instead, Python, for example. Now the not a number row. It has the same all ones exponent as infinity, but this time the significand is non-zero. That combination is NaN, short for not number. It marks a result that is undefined, not merely huge. 0 divided by 0, infinity minus infinity, the square root of minus 1. NaN has 2 famous properties. First, it is contagious. Most ordinary arithmetic that touches a NaN produces a NaN, so an error propagates all the way to the final result instead of hiding behind a plausible-looking number. Second, and stranger, NaN is not equal to anything, including itself. Testing a NaN against itself gives false. That is a handy test. A value not equal to itself must be a NaN, but it also breaks any code that compares floats with plain equality. The last row is the most subtle, subnormals, also called denormals. The stored exponent is all zeros, but this time the significand is non-zero. Without subnormals, there would be a surprisingly wide empty gap between 0 and the smallest normal number, and any tiny result inside that gap would snap straight to 0, losing all its information. Subnormals fill that gap. They break the normalization rule. Instead of an implicit leading 1, they use a leading 0, 0.fff, which lets them represent values much closer to 0, though with fewer significant digits. The payoff is gradual underflow. As a value shrinks toward zero, it loses precision one bit at a time, rather than dropping off a cliff. This keeps an important promise. A minus b is zero only when a truly equals b. Floating point is powerful, but finite. Now we face what finite precision actually does to your calculations, and how to write code that survives it. This is the defining picture of floating point. The representable values are not evenly spaced. Near zero, they cluster densely. Far from zero, they spread far apart. The reason is the exponent. Each power of 2 octave from 1 to 2, from 2 to 4, and so on, holds the same fixed count of representable values. So as you move to a higher octave, that same count is stretched over twice the width, and the gap doubles at every step. Here the gap near zero is 1/16, while farther out it is 1/2 8 times wider. Precision is relative, not absolute. The same number of significant digits at every scale. Machine epsilon captures relative precision in one number. It is the gap between 1.0 and the next float, about 1.19 times 10 to the minus 7 in single precision, where epsilon is 2 to the minus 23rd. For double precision, it is 2 to the minus 52nd, roughly 2.22 times 10 to the minus 16, which is why double gives about 15 or 16 good digits. And for normal values, epsilon scales. For any normal value x away from zero, the gap to its nearest neighbor is about the absolute value of x times epsilon. The larger the number, the larger the absolute gap, which is exactly why small values get lost when you add them to big ones. Subnormals near zero are the exception. Down there the spacing is constant instead. Of all the floating point traps, catastrophic cancellation is the most dangerous. It happens when you subtract two numbers that are nearly equal. Look at A and B both are known to 15 significant digits, and they agree in the first 13. When you subtract, those 13 shared leading digits cancel to zero and contribute nothing. What survives is only the last two digits, the part where A and B differed. So a 15-digit input became a 2-digit answer in a single step. The subtraction itself was perfectly exact. That is the cruel part. The inputs already carried tiny rounding errors in their low digits, and after cancellation, those low digits are all that is left. The fix is to restructure the math so you never subtract two nearly equal values. Now back to the puzzle from the very start. Why is 0.1 plus 0.2 not 0.3? Pause for a second and predict. What will Python print, and will it be equal to 0.3? And there it is. In double precision, the sum prints as 0.3 followed by a long tail ending in a 4, and the test against 0.3 returns false. The reason? Neither 0.1 nor 0.2 has an exact binary form, so in double precision each is rounded to 53 significand bits, and then their sum is rounded once more. Those roundings leave a tiny, genuine leftover. The lesson is blunt. Comparing two computed floats with double equals is almost always wrong. So how should you compare floating point values? When rounding error may separate two results that should match, don't test exact equality. Ask instead whether they are close enough. Within a tolerance you pick for the problem. The first way is an absolute tolerance. Check whether the absolute value of a minus b is below some small threshold. That works when you know the rough size of your numbers. The second way is a relative tolerance. Scale the threshold by the larger of the two magnitudes. That works across many scales, but it breaks down near zero, where both magnitudes are tiny. The third way combines both, and that is what Python's math.isclose gives you. For most everyday work, isclose is the right default. Near zero, set an absolute tolerance as well. Let us gather what this chapter gave you. 4 takeaways. First, fixed point locks the binary point at one agreed spot. It is simple and fast, but range and precision must fight over the same bits. Second, IEEE 754 lets the point float across 3 fields, a sign flag, a biased exponent for scale, and a mantissa with an implicit leading one for the digits, combined by the formula. Value equals minus 1 to the power s, times 1 point mantissa, times 2 to the true exponent. Third, the special values spend the reserved exponent patterns on positive and negative 0, positive and negative infinity, not a number, and the subnormals that give gradual underflow near 0. Fourth, precision is finite and relative. Machine epsilon sets the relative step. Catastrophic cancellation can destroy it in one subtraction, and you should usually compare computed floats within a tolerance rather than with plain equality. That is Chapter 4. You can now store fractions in fixed point, float the binary point with IEEE 754, decode a real 32-bit pattern by hand, recognize 0, infinity, not a number, and subnormals, and reason clearly about precision and its pitfalls. So far, everything has been a number. In Chapter 5, we ask a completely new question. How does a computer store a letter or a punctuation mark? The answer begins with ASCII, the encoding that gave every character a number. See you there.